Hello, this is online lecture number 2 of multivariate analysis, EPSY 905, this spring 2018. And this is a continuation of the first lecture where we talked about descriptive statistics, univariate and multivariate. Now we're going to get into a review of the general linear model. As you recall, the general linear model is something that we would use to describe what a regression or analysis of variance type of model might be. And today we're going to cover regression, ANOVA, analysis of covariance, and then things beyond that when we talk about interacting terms. And I'll review what each of these features happens to be, or what the features of each model happen to be that give rise to each of these names. And really what this is describing, though, is we're going to talk about the conditional distribution of our dependent variable, conditional on a series of independent variables or predictors as we go forward. So let's begin. The general linear model incorporates many different labels of analyses under one unifying umbrella. And so let's take a look where we're at today. Whoops. We're here in univariate land where we have a single variable y. If we take a single variable y, now this y is supposed to be a continuous variable. It doesn't have to be normally distributed. We're going to talk about the assumption pretty soon, but it's continuous. If we predict it using categorical or discrete integer valued predictors, x being a predictor here, we usually apply the label of ANOVA, analysis of variance. On the other hand, if we use continuous predictors, then we usually apply the label of regression. And if we use both types, continuous and categorical, often we get the word ANCOVA in there, but that usually is for when we have main effects of each of the continuous and categorical predictors, but not their interaction. When we put their interaction in, which is where we'll end this lecture today, that is a different type of model altogether that doesn't even have a name, but it's much more plausible, I think, to me. Now, because this is a multivariate class, we'll see that there are multivariate analogs of each of these names. So multivariate-wise, so again, you've got multiple continuous dependent variables that you'd like to predict. If you have categorical predictors, we put an M in front of ANOVA, making it multivariate ANOVA or MANOVA. If you have continuous predictors, we put multivariate in front of regression. We wouldn't call it regression, but multivariate regression seems to do. And similarly, if we have both types, we'll call it MANCOVA, or multivariate analysis of covariance. So typically what we assume in each of these models is that the error term is normally distributed. So that means that the data themselves follow a conditional normal distribution. That doesn't mean that the data are normally distributed marginally, right? That would be like something you could look at with a scatter plot or a histogram that, not a scatter plot, pardon me, a histogram of a variable marginally. Remember that weight distribution that we saw before was bimodal. We're going to be predicting weight today. That is not normal, but that's okay because what we're looking at is the conditional normal distribution. That's what needs to be normal. Get more in that in the slide as we go forward. The models, now what happens if you have non-continuous or non-conditionally normal outcomes? So perhaps you had a dichotomous variable, or you had a type of count variable, or they're censored variables where you have a number that ranges between, let's say, 0 and 1, or 0 and 100. Now, those types of outcomes, those types of not necessarily continuous outcomes or bounded continuous outcomes, if we want to model them or we want to predict what their values might be, that would fall under another class of model, something called the generalized linear model, whereas continuous outcomes typically fall under the general linear model. So it's another term. We're going to get to that in a future lecture. So what is the general linear model? Let's take a look here. Let's imagine we have an outcome here, y. The subscript p stands for, this is person p's observation or variable y, something we've observed about person p. And the model itself says we're going to set this equal to beta 0, which is our intercept, plus beta 1, a regression coefficient, times x, plus beta 2, another regression coefficient, times z for that person, plus beta 3, another regression coefficient, times the product of x and z. In this case, the product of x and z represents an interaction between the variable x and the variable z, an interaction between predictors, whereas the variable x by itself here represents a main effect of x, and the variable z by itself here represents a main effect of z. The part in the Illinois orange section here represents the model for what we call the means. This provides us the predicted value. Technically speaking, it's the mean of the predicted values for a person with a given x and a given z. So here, that is that box. That's what gives us our prediction. That's what gives us our regression line for each person. In the blue box is the model for the variance, right? Error. And error is said to follow a normal distribution. This term right here, this tilde, says error. Each person has an error term. Once we predict their observation, what's left over falls under error. What's the difference between predicted value and actual value is error. So E sub p, each person's error, follows, this tilde means is distributed as, has a normal distribution, or each comes from a normal distribution, where the mean is 0. The mean being 0 is non-negotiable. It allows us to have unbiased regression coefficients. But we also have a residual variance. So this talks about if we were to look at the variance across all of our people, right? So we do a prediction, we grab their error terms, how much variance is left over once we predict variables is this sigma squared E. If you had a linear models course and we talked about mean square error in an ANOVA table, that is what this term, where this term comes from in the old way of doing things. We're going to have a new way of doing things where we estimate it directly, but that is it, residual variance. So here we're going to come back to this much more in the future, but right now just understand that this normal distribution has two terms, one for the mean, one for the variance, and that our assumption follows on error. So when I talk about conditional normality, here's what we're saying when it comes to regression. We're saying our dependent variable is the result of a series of predictors that we make no assumptions about. We make no assumptions about x or z or the product. They do not have to be normal. They do not have to be continuous. They can be categorical. They can be continuous. They could be whatever. We make no assumptions about x and z or the predictors. Further, we're making no assumptions about each of the regression coefficients. They just happen to be. So when all this term in the box right here represents is a constant, if you add it all together, that predicted value is a constant. And when you couple that constant with this random variable that's normal with a mean of 0, it means that y itself is thought to have, or the conditional distribution of y, once we condition on x and z. So given a person's x, a person's z, y follows a normal distribution with a mean equal to what's in the orange box here, up here, and a variance equal to sigma squared error. So that's it. What that means is, for checking your variables for normality before you do your analysis, particularly y, it's unnecessary. You do not check before the analysis because it's not the marginal distribution we're worried about, it's the conditional distribution, which only can happen after the model is run itself. So now we're going to begin to build a linear model for predicting a person's weight using a person's height. Now, let me flip over to the R package I have here. This right here has pardon me. Here's the R package. It has, we load our library, we load the data height and weight, sex, height, weight. This is our data set from before, and we create dummy coded values. So again, this is 20 observations, 10 female, 10 male. We have their height, we have their weight as well, and we've dummy coded a variable to be called female. So anybody who's a female gets a 1, Anybody who's a male has a 0 on that variable itself. So we're going to begin our analysis by we're going to begin building a linear model for predicting a person's weight using height and gender as predictors. And what we're going to do is we're sort of doing this in an odd way of proceeding. We wouldn't normally do this progression if we were analyzing our own data, but I'm doing this for didactic reasons. I'm trying to teach you a little bit about regression, a little bit about ANOVA within the context of the general linear model. But our first model is a good one to run, and this is something that connects models to data. It's something called an unconditional model, an empty model. We're going to provide a model for weight with no predictors. And we're going to see that what comes out of that model are numbers that we would see in descriptive statistics as well. But then we're going to end up with an ending model that is one where we have all predictors involved plus an interaction involved, something we're going to call a conditional model. So let's begin with the empty model. Model number 1, we're going to take a weight of a person, weight sub p, and we're predicting it with nothing. So it gets an intercept, and it gets an error term, which is an odd way to start. But let me show, there's a reason for this, and we're going to do that in just a moment. In R, the code to run a linear model is the function lm. It's built into R itself. If we were to look at help for the lm function, here's what it would look like. It's just fitting linear models themselves. So it begins with having a formula. The formula takes the dependent variable on the left side, puts tilde in between it and the predicting, and on the right side you put your predictors. But because we don't have predictors here, we're just going to put the number 1, which represents the intercept. Or another way of thinking about it, beta 0 is multiplying a 1. The 1 is for everybody. It's like this dummy-coded variable. Everybody's part of the data itself. So we put that in, we save it as an object. We're going to call that model 01. It runs without errors, and if we want to see the summary of it, we have to submit model 01 to the summary function. And this is what we see here. We have an estimate of the intercept of 183.40, standard error of 12.61. So there we go. Well, if you remember our data, if we were just to take the mean, I use the mean function here, of data 01 star weight, LB, take a look. The intercept represents the mean. So what we're saying with the empty model is that if we were not to predict a person, if we didn't have anything to predict a person's weight by, what would be our best way of predicting them? What number would we use? And that's where the measure of central tendency comes into. The mean is a very good measure. What the model is saying is the best measure for predicting what someone's weight should be. In fact, that mean is 183.4. Now, similar to this, we see that the error, the residual variance here, or pardon me, the error, standard error of the mean, we talked about standard errors in the previous lecture. This is how much, if we were to repeat this sampling process of 20 people over and over again, this is how much the means would vary, the standard deviations of the means, of 12.61. And sure enough, where that comes from is the standard error of the mean itself. Furthermore, we could go and look at an ANOVA table using the ANOVA function and find that the mean square error is 3,179.1, and if we were to compare that with what we saw before, did not give a standard error for this, by the way. In our future models and methods, we will have standard errors for the variances as well. We could tell that this is equal to the variance of the dependent variable. Right? So our variance is 379.095 here. Our mean square variable is 3179.1. What am I trying to do here? I'm saying basically it's this. If you have nothing to predict, what a regression model will give you is a mean and a variance as its parameters, beta 0 and sigma squared. Beta 0 is the mean of the data. How much error in that is how much error is in the sample already to begin with, and that moves us into another conversation, which is every time we now add a predictor, that error will shrink if the predictor allows us, it has some type of information about the dependent variable. So let's add a predictor. We're going to take height and put this in the analysis as well. So weight is equal to beta 0, the intercept, plus beta 1 times height, plus error. So now model 2, go back into an R. Now in the LM function, instead of having a 1 over on the right-hand side of the tilde, we put height in inches, the name of the variable. The 1 is implied here. It would work the same if we typed 1 plus, but we don't have to. Let's take a look at what this model says about our data. So now our intercept is negative 227.292. What does that mean? Well, the intercept is always going to be the value that we predict a person will have when all of the predictors are equal to 0. So a person who is no inches tall would have a predicted weight of negative 227 pounds, which both of which are seemingly impossible. In fact, if you think about how mass works, someone with a height has to have some type of mass. With no height, it's like having no mass whatsoever. This is where the linear model starts to do us wrong. It's sort of interpolating what we think is happening in a far distant part down to when we have 0 mass. It just doesn't make any sense. Now, what we could have done to avoid a nonsensical value is shifted the mean of height. Had we shifted height's mean from, whatever the mean of height is now, but maybe we subtracted that number off, or maybe we subtracted 72 inches off, so relative to 6 feet tall. Now, all of a sudden, the intercept height itself would be 0 at that value, at 72 inches, let's say, and the intercept would represent the height at that value. But we'll have more on centering as we go forward. The regression slope is 6.048. What does that represent? That means for every 1 unit increase in height. So what is 1 unit in height? Height is measured in inches. For every 1 inch taller someone is, we expect them to weigh an additional 6.048 pounds. And again, we have our standard error for that as well. Now, in looking at the parameters with the standard error, what we can find really quickly is that the estimate divided by the standard error is equal to what's in the t-value line. And the t-value of 5.621 also has an associated p-value with it. Right, this p-value is very, very small. The 3 stars represents it having a significance less than 0.001. Here, this would say that this estimate of height is significantly different from 0. So this is a valuable predictor. It helps understand what we end up having. Now, if we wanted to look at the residual variance itself, we can take a look at the ANOVA table. Our mean square residual of 1218 is our new residual variance. And furthermore, what we can see with that is that if we take the difference of our previous residual variance, 3971 minus 1218, dividing by our previous residual variance, we can see that height explained 67.1% of the variance in weight. So the variance shrunk by 60, or the variance before is 61% of itself, just by predicting it with height. Now we can actually do a model comparison. There's the ANOVA function in R. If we give it 2 different models as arguments, what we end up seeing here is the difference in the 2 models. This is an R-squared change test. This also would give us a similar bit of information that we saw previous to this here. Okay, moving on. In fact, what you'll see here is the F value for the degree, the R-squared change is equal to the F value for our predictor in our ANOVA table. So, talking about centering, let's talk about this just for a little bit here. Let's imagine we take the mean height was 67.9 inches. Let's create a brand new variable called height height in underscore MC. What this represents is height in inches that's been mean centered. We create it by taking our original height variable and subtracting the mean. So now here is our new height variable. Here's the values. If we were to take the mean of this new variable, what would the mean of it be? What do you think? The mean would effectively be 0. So now, we put that variable in our analysis, we take a look at our summary, and what changes? All right, the height slope of 6.048 is identical to what we had before. So the slope is not changing when we mean center. However, take a look at the intercept. The intercept is now 183.4, which is our mean of our sample, mind you, whereas before it was negative 227.292. Why that happens to be the case is because what we have done is we've defined what beta 0 happens to be. Beta 0 is the predicted value when all of the predictors are equal to 0. Well, height is equal to 0, not at 0 now, not at 0 inches, but it's equal to 0 because we subtracted the mean height at 67 point, what was it? 67.9 inches. So somebody who's at the mean height of our sample will have a predicted intercept or predicted weight at 183.4. And this is a feature of linear regression in that the regression line always goes through the mean of y and the mean of x. So what we've effectively done is take the mean of x and say that's where the 0 point is, and because of that we've moved the intercept along accordingly. But again, all we've changed by centering is the intercept. We haven't changed the slope, and we haven't changed the residual variance. Where centering is going to make a big difference isn't in this example, although we do have meaningful parameters now. Nobody really cares about the intercept too much. Where it makes a difference, though, is when we have interaction terms. Because the interaction terms, by adding interactions to the model, we make our main effects now conditional on the values of the other terms. So we see a lot of centering in models where interactions are present. And we'll get to that at the end of this class. Then we have an entire lecture coming up dedicated to interactions where you'll see this much more thoroughly. So again, here's our fit plot for weight predicted by height. This looks okay, although if you look here, there seems to be a group of people up here and a group of people down here. So we have this weird pattern of residuals. So perhaps we could modify this slightly. But let's first look at our numbers one more time. We can create hypothesis tests for our parameters to determine whether or not so this is a null hypothesis significance test type of framework where we're going to allow this to test whether or not our regression slope is equal to 0. The null hypothesis is that beta 1, the slope of height, is 0. The alternative is the slope of height is not 0. And we have two options for this test, both of which give the same numbers. One is to look at the ANOVA table, the F test, and that was given by, if we did ANOVA, right here, that's our F test. The other is to look at what we call a Wald test, which is not exactly a Wald test in this context because it's a t-statistic, but it's functionally a Wald test. We're going to call it a Wald test, which is, again, the estimate divided by its standard error. Why that's a test statistic, we're going to talk about coming up because it's involved in maximum likelihood as we go forward. But effectively, if you look at the p-value here, these are identical, even though they're identically small. And furthermore, this is where you get t squared equals f. If we took 5.621 and squared it, we get 39.5, roughly 39.53. There's a little rounding error in the process of squaring and rounding numbers there, but that's where that goes off. So our conclusion here, because the p-value is very small, is that our slope is significant. We reject the null hypothesis. Hooray. All right, so that was regression. Let's imagine we started, instead of regression, we started with the idea that we're going to predict this based on which sex a person might have. So here we have the weight of a person. It's being predicted by an intercept. But now we're not putting in weight, or height, excuse me. We're putting in the sex status. So in this case, we put in our female variable. It has its own regression slope. I'm calling it beta 2 here because we're going to combine these two models in our next model, model 4. And beta 1 will be our height slope as well. But we still have error, and we still have a residual variance that is associated with error. Now, because gender is or sex is a categorical predictor, we first have to code it into a number before entering it into the model. Now, this is typically done automatically in the software, but I'm going to move us from that in R for right now because that involves a class of variables called factors that we'll talk about in later weeks. Factors are really, they really start to interfere with learning R when you're just getting into it, I think, although they are very powerful and will be used later on in what we do. But here we're going to dummy code the variable. We're going to say everybody who's a female is a 1, everybody who's a male is a 0. This matters because now that sets very specific meaning to each of our parameters. So if we go back to our R code, we now see in model 3, we're taking weight and predicting it by our female variable. And our results are shown here. Intercept of 235.9 and a weight slope of negative 105. So how do we interpret that with a categorical variable? Well, the interpretation is technically identical. However, we use a few different words to describe it because the predictor can only be a 0 or a 1. So let's take a look at the intercept. 235.9 represents, again, just like regression, it represents the predicted value when all the predictor variables are at 0. But because we know the female variable happens to be 0 for males only, we know that this is the predicted value of males in the sample. Or moreover, this is the mean of males in the sample. So it's the mean height, the mean weight of males. So now the slope again represents the change in the predicted value for every 1 unit change in our analysis. But because female only has 1 unit, the units are 0 and 1. This really represents a different group. It's saying that the mean for females is 105 pounds less than the mean for males, or 235.9 minus 105, which gives us 130.9. So that is what the slopes get interpreted as. So again, when we have a categorical predictor, we typically use the word saying it's a difference in mean. But it's identical to saying for every 1 unit change, the change in the predicted value is given by the regression coefficient. It's identical, but because there are only 1 unit in the category, in this dummy code there's a 0 or a 1, we're allowed to say it's a difference in mean for the two groups. Now, similarly, we can take a look at the p-value. There is a significant difference here saying that men and women have a different weight, average weight. We could also look at our residual variance. Here now it's down to 293, which is very small. What we'll see is that our residual variance, our gender, explains 90.8% of variance in weight, which is very large. In fact, you can see that right here. So that's very good. However, so this is kind of going a little bit more thoroughly here, breaking down what those values mean. Gender is coded using what's called a reference group, or a dummy code. The intercept becomes the mean of the reference group, in this case the 0 group, males. And then the slopes are now the difference in means between the reference and non-reference. So when we have a categorical predictor with C categories, in our case 2 categories, there are C minus 1 predictor variables created. Each of these could be dummy coded. So for us, we had the female variable, only 1. So 2 minus 1 equals 1, 1 variable we created. Had we had 4 categories, we would have had 3 predictor variables. Each one of those predictor variables represents the difference in that group's mean. The regression coefficient multiplying each of those predictor variables represents the difference in that group's mean from the reference group's mean. So the neat thing is, though, the choosing of of which group is the reference group is an arbitrary choice, but it doesn't matter because we can always recover the means regardless, based on our model parameters themselves. So all modeling choices can be recovered. So for instance, the predicted weight for females, in this case it's when the female variable equals 1, is the sum of beta 0 plus beta 2, or 134.5. I put in the wrong number in my R code over here to make this work. And our predicted weight for males then is 100 and, somewhere I have a discrepancy in my numbers. There we go. It's right here. 235.9 There we go. Get my numbers right here. Our predicted weight for females is 130.9, which is the intercept, 235.9, minus the regression slope, 105. And then the weight for females is 235.9 as well. There we go. So my question for you is, what would beta 0 and beta 2 be if we coded male equal to 1? Beta 0 then, if male is 1, the reference group or the 0 group is female. So beta 0 now becomes the mean of females, or 130.9. Similarly, beta 2 would be the difference in mean, or what we have to add or subtract from that mean, 130.9 to get the mean of males. So it will be positive 105. And sure enough, what we can do in software, we can get the mean of these all at once using these beta coefficients. What I'm going to teach you to do this year is once you code a model, even though you've arbitrarily chosen which group is 0, you can always recover group means for any different combination just from the model parameters themselves. We're going to get into that in the weeks to come. So here's a prediction and plot for each of these. You see the difference between groups. All right, let's move on to Model 4, predicting weight from height and gender without an interaction. This is something we'd call an analysis of covariance model. So we're going to take our linear model, we're going to take weight for a person. It's going to be equal to an intercept plus a regression slope times mean centered height for that person, plus a regression slope times the female status of that person, plus error. So we're going to be estimating three mean parameters, beta 0, beta 1, beta 2, and then a fourth parameter of sigma squared error. So now we can go into R, run Model 4. We see our output here, and now what we get to see is the intercept. What does the intercept represent? Again, same thing that we've talked about in our progression. The intercept is the predicted value when all of our predictors are equal to 0. Well, height is predicted to be 0 at 67.9 inches. So this is the mean value for a person who is 67.9 inches and male, because 0 for female represents a male. So this is all males who are at 67.9 inches tall have a mean weight of 224.25 pounds. What does the regression slope on height represent? That represents for every 1 unit increase in height in inches, a person's weight is expected to increase by roughly 2.7 pounds across all people, regardless of whether you're male or female or otherwise. And finally, what does the female slope represent? Well, again, because female is a grouping variable, this represents the mean difference in weight for females and males. And because there's no other terms in the model, this is across all males and across all heights. So what we're expecting in this analysis of covariance is that regardless of a height of a person, we expect a female to weigh 81.7 pounds less than a male. Sort of an odd way of putting things, but that's how it works. We can also look at our residual variance, which is down to 16. You can tell these are simulated data. Our R-square value is massive. It's 9.99. Now, what we can end up doing, because we have these two groups, we could end up forming regression slopes for females and males, predicting their weights. And so how do we do that? Well, let's take a look for females. The F variable is a 1, but we're going to allow that to be we're going to plug in a 1 here for F, but allow height to vary because we want to plot weight versus height. And when we do that, 2.708 times the mean centered height, the intercept becomes 224 minus 0.81, or 142.544. That's the regression line for females, predicting weight from height for females. For males, you'll see the similar process happens, although we don't see for males, the F variable is 0, so we get our regression line of 224.256 plus 2.708 times height. And you'll see between the two sexes here, The only thing that differs is the intercept. The slopes are identical. And we could even plot that. Here's your slope. Here's your males with the higher intercept. And here's your females, the low intercept, and you see those lines are parallel. And so this is one of the things we used to talk about in a linear model class, that the analysis of covariance would make the assumption of the homogeneity of slopes across group, so that each group has the same regression slope. Now in our model, that looks like a pretty good assumption. There's only a few data points that these lines don't fit, but we can go and test that. And in fact, we can build a better model to test that by adding another term that we'll add very shortly. Actually, we'll add right now. So if we wanted to test the assumption of homogeneity of slopes, we would add to our model. Remember, this was the ANCOVA model, beta 1, beta 2, beta 0. But if we add to that the interaction of height and female, we now have a new regression slope, beta 3. So now we're estimating 4 slopes and 1 residual variance, or 5 parameters. We now can see how this changes things, and it makes things all sorts of different with our description. Our model 5, if we look at our summary, let's take a look at what this means. What does our intercept mean? Same thing it meant before. The predicted value when all predictors are equal to 0. Well, this is for a person whose height is at the mean height, 67.9 inches, a person who's male, and because the interaction is comprised of these 2 other variables, it will be 0 if either of the 2 other ones will be 0. So we are looking at a male at 67.9 inches has a mean weight, or expected weight, of 222.18. Okay, so that's pretty straightforward. When we get to the main effects, things start to get crazy. Well, more complicated. The height, the main effect of height, as we see it in the output here, is often called a simple main effect, or a conditional main effect. It's conditional because height appears not only here, but also here in the interaction. We have to look at this number as being the predicted value when the other variable in the interaction is equal to 0. So what this represents is the slope for height for males, right? So when this female term is 0. And why we have to do that is because if female happened to be 1, right, then the female term will go away, and we have 2 numbers, negative 1.09 and 3.97, multiplying the same variable. So we do a little bit of factoring where we combine like terms, and sure enough, our height slope changes. What the interaction is doing is allowing a different slope by group. So to describe the main effect means we have to describe it when the interacting variable is equal to 0. So this, therefore, happens to be the slope for males. You may be asking, what is the slope for females? We'll get to that in just a moment. Similarly, when we look at the female group, this is no longer just the mean difference between males and females. This is now the mean difference when the height variable is equal to 0, because height appears in the interaction with female as well. So for a female, back up, for a person who is at a height of 67.9 inches, right? That's when height IN_MC is equal to 0. Right? For a person of height of 67.9 inches, we expect males or females to weigh 82 pounds less than males. Right? Once again, for a person at 67.9 inches, we expect females to weigh 2719 pounds less than males. This is part of the reason why, if you've in other classes, you may have been told we disregard the main effects whenever there's an interaction in the model. I disagree with that approach. The main effects are very relevant. Why we do not disregard them. However, we have to take the numbers that we see in the output not literally often, because if we didn't mean center our variables, the numbers that we see might be on a different location altogether. For instance, had we put in, instead of mean centered height, let me just run the model with non-mean centered height here in it, model 06, and if I type summary, so now what we see, all sorts of things happen. I didn't take, that's the problem with on-the-fly model modifications. I did not put the right main effects in. There we go. Now let's try it. Now take a look at the numbers. Model 05, our previous model with mean centered height, had a mean difference of 82 pounds when a person was 67.9 inches tall. If we did not center the mean for height, now that number is negative 7.991, so this is saying this is a mean difference of 7.9 pounds, which looks very different than 82.27 pounds. But it's very different because it's now conditional on where 0 is, or a person who is 0 inches tall. We would expect a person at 0 inches tall to weigh about 8 pounds less, female to weigh about 8 pounds less than a male when they are both 0 inches tall. And that's the crazy thing about interactions. The value of 0 depends on what the main effect depends on is the value where 0 is in the interacting variable itself. All right, we'll go back to our model that we had with the mean centering because that's more common in these types of approaches. And we have one parameter left to describe, and now that happens to be the interaction. So there are two ways of describing this interaction. Let's start with the regression slope. Okay? So the regression slope that we saw here was for males. It was 3.1897 plus 1.0939. 3.1897 was the slope for males here. Now, what is the slope? What this interaction describes is the difference, because female is a variable that represents a group. We can say that when female equals 1, so let's take a look here. Slope. Let's do a little R calculation. Male slope equals 3.1897. What is the female slope? Well, we put female as 1 back in our model. We go back over here. When female equals 1, we have beta 3 multiplying height, or mean centered height, and we also have beta 1 multiplying it. So really we take beta 1 plus beta 3, right? So we go over here, or negative 1094 plus the slope for males, and we see that our slope for females is 2.096. So this says that for every additional pound, the interaction is saying that females have a slope that's 1.094 less than males. Right? So you can see the difference here in our result, right there. Another way that we could interpret that interaction is it's a little bit harder, but it's to think about the interaction being the difference in let's see here, pardon me. Well, I'm going to leave it at this for right now. So the interaction itself is modifying or moderating the main effects, as we see. Now, here, I'll give you the other term. The other way to look at it is how does this interaction modify the slope or the difference in means between males and females? So what is it saying? Okay, so this interaction now, if we were to go and take height MC and allow it to vary, right? Let's imagine we have height in inches. Let's put that number at 1. Let's put a person who is 1 inch taller than the mean, or 68.9 inches. They would have an additional contribution to the model of 1.09, negative 1.09 from this interaction. Well, because what we've ended up doing in this is plugging in a person with a 1 right here, right? What this interaction is doing, because female still exists, it's moderating or modifying the main effective female. It's saying effectively that for every additional inch in height, the mean difference between males and females decreases by 1.09 inches, right? Let me say that again. If we were to look at it from the height perspective, as we vary height, for every additional inch taller a person happens to be, the mean difference between weights shrinks, or actually gets more negative, right? So females weigh much less than taller females weigh much less than taller males. And that's what interaction is. It's a really complicated term. That's why we're going to dwell on it a lot these first couple weeks, because interactions show up everywhere in statistics, and they're so powerful that very many people skip over them. So complicated, so many people skip over them, but they add so much to the story of what happens in an analysis, because now you're conditioning on different levels of the variable. So once again, this interaction can be described in two ways. We can describe it as relating to the height variable, so this is the difference in slope for males and females, or it could be the change in the mean difference for males and females as we go forward. So again, there's our regression lines, and what we end up seeing is that we predict, or we explain 99.9% of the variance in weight by height and sex. Now that's clearly, this is simulated data. We would never have an R-square that high. I typically call that Hall of Fame R-square level right there. But if you see something like that, let me know. I'll put it in my R-square Hall of Fame. So if we were to compare, one last thing we might want to do with our data is to compare across models. We wanted to say, what is the total effect of height? When, if we were to look at the main effect and interaction, we could calculate an R-square for each of these, right? So imagine we look at height. Well, let's take our final model, which is model 5 here. This is the one we want to use. By the way, I should also mention that once we get to model 5, what we can see with model 5 is that model 5 fits better than model 4. And model 4 fits better than model 3 and model 2. So at the end of all this process, we don't even need to describe anything from models 1 through 4. Perhaps model 1 because we have our baseline weight. But model 5 is where we use all the parameters to describe all the information about the model. This is like our results section right here. Everything about it. We don't necessarily have to describe other models because they're all subsumed into this model. This model is shown to be more effective, or all the parameters are more necessary. They're all significantly different from 0. So when we get into that, we can compare. May want to talk about the contribution of height by itself. So what we want to do is compare the R-square, or the residual variance, from a model where height is in model 5 with height, to a model where height is removed. So we take height out here, and we take out the interaction, which was model 2, model 3, and we can see that once we add height explains 90% of the variance that's left over in weight that was left over after gender. Now, similarly, we may want to talk, or sex, excuse me. We may want to talk about the total effect of sex on the main effect and interaction as well. Similarly, what we'd have to do is go back to a model that had sex involved and compare that residual variance with the model that is model 5. And here we can see that gender explained 99% of what was left over variance after we had already predicted it with height. So overall, this is what we do in linear models. We'll have a lot more to discuss with these, though, because they are not going away anytime soon. Finally, about weight. Remember in the very first lecture I showed you the marginal histogram of weight where it was bimodal, and I said, should you be worried about this? And I said, hint, no, you shouldn't. Remember, the regression analysis does not assume normality marginally. It does not assume that this distribution of weight, this graph on the bottom left here, should be normal. Instead, it does a conditional distribution. What does conditional mean? It means once we've predicted everything, what's left over should be normal. Or another way of putting that is our error term should be normal. So now once we predict everything, if we look at our residuals, we could take a look, impose a normal distribution over the scatter plot here, and we see it's a little bit better looking for normal. Still not great, but it's still there. So just remember that as you go on, we don't want to transform our data if we don't have to. And in regression or linear models, we absolutely don't have to unless we have some type of issue with our residuals, and rarely is that the case. But certainly we may have data that are very bimodal as we go into it, and we don't want to modify those, because what we end up doing when we transform those is to try to pull these two different groups back together. We'll lose our effects that we're interested in. So transforming the data by and large is not a great idea. But that's it for now, and I hope this lecture has been informative. Again, if you have questions, rewind, listen again, or definitely put your feedback into the online course forum in Blackboard, where you can do so anonymously if you'd like, and we'll discuss it in our next in-person lecture. Thank you.